Today we will be taking a look at electric flux and Gauss's law. Imagine we have a surface. We imagine a line penetrating the surface. This line forms a right angle with the surface so that the line is perpendicular to the plane that the surface creates. Now imagine that we have an electric field close to this surface. We can measure the flow of the electric field through this surface as electric flux. To understand flux a bit more, imagine we have a cup and a water faucet. When we turn on the water and the cup is held completely flat, the cup is filled with water. Were we to hold the cup at an angle, though, the cup would only be partially filled, as some water would drip out from the side. Were we to hold the cup at a 90-degree angle, no water would enter the cup, all of it would fall past. We can consider an invisible surface over the open end of the cup. This is equivalent to the surface area we measure with electric flux. Depending on the angle that the surface makes with the faucet, varying amounts of water can be held by the cup. Gauss's law sometimes allows us to simplify electric flux problems. When we are measuring the flux through a closed surface, we say that the electric flux through that surface is the amount of charge enclosed by the surface divided by epsilon naught. As long as the surface is closed, its shape doesn't matter. This is because we can draw another surface that encloses the same charge. These two surfaces will have the same flux. For example, here we draw a sphere, for which every point on the surface of the sphere, the electric field is perpendicular. To demonstrate this concept, we consider these three figures. In the first, every charge is enclosed by the surface. We have 3 positive charges and 2 negative charges within the surface. Flux for a closed surface is the charge enclosed by the surface divided by epsilon naught. We have 3 positive charges and 2 negative charges, so the total charge enclosed is 3q minus 2q, resulting in just q divided by epsilon naught. In our next figure, we have 3 charges inside the surface and 2 outside. The 2 charges outside of the surface will make no contribution to the flux through the surface, because every field line that can be drawn from either of these charges will pass in through one side of the surface and out through the other. Thus, the net flux through the surface due to either of these charges is 0. Like before, flux is the total enclosed charge divided by epsilon naught. Here we have 1 positive charge and 2 negative charges, so the net charge within the surface is negative q. In our final figure, we have no charges inside the surface, so without even needing to count or consider any of the charges, we know that the flux through the surface is going to be 0, as there are no charges present within the surface. In our second example, we have a point charge of 5 microcoulombs within a cube. The charge is placed at the center of the cube, but because of Gauss's law, as long as the charge is within the cube, where it is specifically does not matter. We can still calculate the flux through the cube. Using Gauss's law, we take the total charge enclosed, 5 microcoulombs, and divide by epsilon naught. Plugging in our numbers and solving, we have 5.6 times 10 to the 5th Newton meters squared per coulomb of electric flux through the cube.